All right, good afternoon. For those of you who do not know me, my name is Ali Kujuri. I'm an adjunct professor at the Department of Engineering Science and Technology and one of the organizers of this lecture series. On behalf of the School of Science and Technology and the department, I would like to thank you all for coming to this seventh lecture in the series since the beginning of the semester, and in fact the 106th lecture since the start in 2006. I should not forget to thank Agilent Technologies for, the old Agilent Technologies and now Keysight Technology for supporting this lecture series, and also the department since in fact early 2000. And as a result, what I usually do is to invite the first invited speaker in each semester. Basically I devote the lecture to one of the expert speakers from Agilent Technologies. Before I introduce our guest speaker for today, let me mention that there are we have ordered pizza, which is going to arrive at 5:30 right after the talk, and we hope that you enjoy it. Also, the next talk will be on February the 18th, and the title of talk is Bleeding Edge FPGA and Digital Design, New Challenges at High Gigabits Rates, by Mr. Chuck Corley, Principal Digital Hardware Engineer, National Instrument. Our guest speaker for today is Dr. Forrest Kellert, and the title of his talk is Fabrication and Testing of High-Frequency, High-Speed ICs. After receiving a PhD in physics from Rice University, Dr. Forrest Kellert started working at Hewlett-Packard in 1980. He is currently manager in high-frequency technology, order fulfillment, Keysight Technologies. He has been with Hewlett-Packard, Agilent Technologies, and now Keysight Technologies for the past 36 years, working on lasers, photodiodes, and high-frequency and high-speed ICs, and of course also the light-emitting diodes. So here is Dr. Forrest.
Thank you very much, Professor Kujore. Appreciate it. Appreciate the invitation to talk. My daughter is an RN, and she's in the nurse practitioner program here at Sonoma State, so I have to make sure I don't embarrass her with the talk. Please ask questions as we go along. Don't wait until the end. If there's topics to discuss, let's bring them out and have a good discussion. I also want to thank Professor Estrick. He was involved in Hewlett-Packard, Agilent, not Keysight though, because you were here before Keysight. So Don will probably correct any errors that are made. One of the, I think it's kind of funny, the jokes I tell when I'm giving tours is, I say, as Professor Kujore said, I started working at Hewlett-Packard directly out of graduate school. When I finished there, and during a tour I say, I'd like to tell you it's a great place to work, but I've never worked anywhere else, so I really don't have a point of reference for comparisons. So the title of the talk is Fabrication and Testing of High-Frequency, High-Speed Integrated Circuits. The outline that I'll follow is shown here. I need to give you a little bit of an introduction to Keysight Technologies. And I think it's important to set in context the work that we're doing actually in Santa Rosa on the Fountain Grove Parkway. And it's unusual to actually have a fabrication facility like that in this part of the country. And so I spend a lot of time explaining why it's so important, our contribution to the company, and that helps them understand why it's so expensive, what we do. But the contribution is a good trade-off, and I'll share that with you. I'll move into why we need high-speed, high-frequency ICs, talk some about the fabrication, then the testing, and then I'll finish up as Professor Kajuri invited us, a little bit about future trends, and this may take you a little bit off guard. It's not so much the technology trends as the needs of an engineering community moving forward at this time in our world. And then I have questions at the end. I'm happy to do them then, but as we go along is fine too. All right, so just a few of these are canned slides from the company. The way the company, so we've been an independent company for about a year and 3 months or so. So a lot of this is evolving as we figure out our place in the world. It's a new company, but it's built on 75 years of experience. And it started back right before World War II with Bill Hewlett and Dave Packard as Hewlett-Packard. So that's where the name came from. And it then continued we were spun off from Hewlett-Packard in right around 2000, late 1999, 2000. And for the next 15 years or so, it was Agilent's electronic measurement group. And you go, well, why be that specific? And it's because the other part of Agilent was the life science business. And so in both cases, with Hewlett-Packard, they were interested in pursuing computers and enterprise solution, and we were a distraction. Even though it's the way the company started back in 1940, the electronic measurement was not what they wanted to focus on. So they spun us off as Agilent. In the intervening years, Agilent built up a very strong, what they call life science group, which is more of the type of instruments you'd find in your biology building. NMRs, chemical gas chromatograph types of analysis, drug testing, eventually moving into DNA sequencing. And guess what? The electronic measurement part was a distraction to the life science. So about a year and a few months ago, we were spun off from Agilent, and now we're Keysight Technologies. And as it says here, we're very focused on helping companies do their toughest electronic design and test issues and get them a solution quickly. So that's Keysight Technologies. It's a made-up word. It's the only way you can get a website is if you make up the word. All the real words are taken at this point. And it's a combination of key insight. And so you've got Keysight Technologies. So again, these company slides are saying that we are helping folks get electronic products to market faster and at a lower cost. And the types of folks that need our solutions are illustrated in these little figures. I mean, some of the ones are very traditional in terms of electronics. You would guess that a company involved with radar would need state-of-the-art electronic measurement tools. Some of them less obvious, how to make the contribution to cloud devices and automotive electronics. But that's the goal of the company. And the goal is to help our customers simulate, prototype, which means make models of, and then manufacture and then optimize for getting parts, components, electronic products to the market faster and at a lower cost. And this is the only equation in the whole talk is up here in the company slide. And it's indicating that the traditional role of Agilent Technologies has been in hardware, and they call that product leadership. They would like to combine that with a powerful software franchise. and bundle that with services, and all of that will lead to solutions for our customers. So hardware plus software plus people equal insights, and it's Keysight, so key insights is what we're after. Now remember, I'm going to be talking about the role of integrated circuits to the hardware piece. Software is a way to make those hardware solutions more effective for our customers. And I want you to remember the people piece, because that's what I will return to at the very end of the talk in terms of opportunities for all of us here as a trend moving forward. Okay, so in the hardware market, we do support electronic computer-aided design. These are, the specific offering is called ADS, and it's a way of designers using this tool to simulate discrete components, full ICs, entire block diagrams, and then from those simulations, getting a good idea of what's actually going to happen in the real world when they actually fabricate these components. And it's computer simulation software, and it's augmented with very good models that can be extracted in the laboratory to bolster the predictive capability of the models. In the hardware end, I like to think of them as very sophisticated receivers. Our word for that is called signal analyzer. And these are extremely sophisticated. I'll give you a taste for it as we go through in the talk. But they go to very high frequencies. They have a whole lot of functionality built in for very sophisticated analysis of the signals, and firmware and software that make them even more powerful. Same thing, but with transmitters, and we call those signal sources, offered in a variety of frequency ranges, but really high frequency, up to 50 gigahertz at this point and pushing further. The combination of those two in one box is a network analyzer. And I don't know if you've had a chance to see those in your laboratory work yet, but those basically have, and we'll see a big blown up picture of a network analyzer. Those have a transmit capability to a black box under test or a device under test. The signal goes through and then comes out and goes back into the same box. And there's all kinds of information that's possible with that type of in-out analysis or measurement. So those are those types. And it's hard to see on this screen, but in each case, they're showing that it's becoming an ever more modular world where a lot of the functionality of these instruments can be incorporated in a little plug-in unit that would go into a PXI chassis. Also, what I don't show in this slide is some of these offerings actually end up in what's called handheld. And they're handheld like this. It's not a cell phone type of offering, but it is amazing compared to these that really do take racks to support. These work in the frequency domain, and that's actually where we're most comfortable over the years. Hewlett-Packard and Agilent and Keysight, our core is in the frequency domain. Very high frequencies in certain cases. 67 gigahertz is the top end at this point, but we're pushing even further with remote heads. Time domain, you guys are probably too young, but early on for oscilloscopes in the time domain, you'd always think of somebody else, not a Hewlett-Packard scope. In fact, when I was back in graduate school, the only way we got a Hewlett-Packard scope was it was given to us. I liked it, it was great, but it's a whole important product line that we attempt to satisfy as well now. So frequency domain, time domain, and one-box testers are much more concentrated in terms of their focus. Boxes that will help you on the manufacturing floor, testing the cell phones, for example, that you all carry. And that's an important point for me to emphasize. As we go further, we're trying to provide solutions for the customers that build cell phones or that build Wi-Fi devices, routers, trying to make sure that they put out the right frequency and the right power, the right noise level, but we don't make cell phones. And it's a completely different market that we're trying to address. And that's one of the reasons why what I'm showing you works. We're very tightly integrated with the designers that know how to do ADS, that are working with the instrument labs to get whatever the latest and greatest solution is that people need in the real world. And those designers have got excellent models for what we can actually fabricate in-house. And what we try to do in-house is what we call bleeding edge technology, which means it's right at the edge of what's really manufacturable. And we do that to provide a competitive advantage. Other folks that might offer these types of solutions don't have access to that technology. And that's what we provide. Okay, so I've already gone into the next topic. So why do we need these integrated circuits? So usually when I give a tour, I spend a moment and I say, have you ever dropped your cell phone and the back pops off and you look inside and there's all these little black boxes and black modules inside? Those are integrated circuits. And they contain many transistors, resistors, capacitors, inductors, all integrated on a single little sliver of semiconductor material. And it was a development back in the 60s, that far back, integrated circuits. Now, of course, they're used all the time in computers, memory, processors, but we have a very special variety that I'll be explaining to you today. We make our own integrated circuits, design and fabricate, because again, it's a receive, transmit and receive scenario. We're trying to get real world signals. So that means very faint signals that people are trying to analyze from a cell phone tower that they're trying to repair, or signals from cell phones that are on a line being tested, satellite communication dishes. The military are always interested in receiving what's going on out in the real world. And for the types of solutions we are trying to provide, we want to acquire those signals, and I say at the front panel or at a remote head, process them, and then down convert in either frequency or speed. And there's a number of different technologies for doing that. You can mix, divide, or demultiplex to try to get those down to lower frequencies or speeds. You then perform an analog to digital conversion, and then process and display with firmware and PC tools. So the italicized point is where we try to make the contribution locally, right here on Fountain Grove Parkway. The ones that are not italicized, we address either in other parts of the company, or we just buy off the shelf. The minute the frequency or speed is low enough, we'll buy, because the proposition that we put forward is pretty expensive, and we need highly skilled people to make it work. Transmit, same thing, but in reverse. We synthesize our data with firmware and PC tools, go in the opposite direction, a digital to analog conversion. We then process and upconvert with either multiplying or multiplexing, and then get those signals out into the real world, to a device under test, to a system that needs to be exercised, or characterization for your lab work. All are possible reasons you'd want to create the signal. And then, as I explained before, you can combine the two in one box, where you transmit, go through a device under test, and then receive and do an analysis on the combination. So that's why we go through the trouble to make our own ICs. What that can look like, I've taken out of a literature publication from from our design manager in our technology center. So it's in the literature, so I didn't have to worry about sharing this one. This is a block diagram for what at the time was the world's fastest real-time oscilloscope. So I said, gee, you don't usually think of oscilloscopes with our company, but the president of our company at one time ran LaCroix Electronics, and he puts it out as a challenge to the whole company. We will not be beaten. And so we come up with innovative architectures like this. So the real world is this way in the figure. We've got amplifiers, attenuators, more amplifiers, triggers, samplers, buffers, and then finally, in this portion, analog to digital conversion. So this is an example of real world trying to get it converted into a form where you can do analog to digital conversions. But at 32 gigahertz real-time speeds, it's very difficult to do that. And this is dated at this point. Actually, our very best now is basically the same architecture, but double the frequency bandwidth, 63 gigahertz. Okay, so you'd say that's interesting. All of the colored boxes on this figure are actual integrated circuits that we make here in Santa Rosa. Custom, done by our own designers, fabricated in our own facility, and it goes down the chain to lower and lower frequencies for processing, but everything is going so fast in the data stream that even the buffers before the analog to digital converters have got to be RICs to cope with the speed. So this gives you a concrete example of real world. Once you can, you do the analog to digital conversion and then do the rest of the processing. But up in the front end, you need our type of solution to deal with those data streams and those high frequencies. And they're not available on the shelf, so it is a worthwhile exercise to go through fabrication of what you see in color here. Okay, so if you're going to do that on a routine basis, here it is stated again, real world, R integrated circuits, then you go to analog to digital conversion, and then processing, often combined with intellectual property, we call it algorithms for doing the processing that our labs often come up with. And one example is if you take a course in electrical measurements, you will have this in and out set of measurements that I described that are called S parameters. One of our engineers said, gee, you know, the mathematics only works for linear responses of the device under test. I'd like to provide a more complete mathematical representation of those results, and so this is David Root, and it's called X parameters. And that's actually part of the name of our latest offering, is PNAX. Okay, so that's the idea behind that set of figures. I'm using the word integrated circuit, and we talked about that a little bit. We have an idea of what that is. Silicon with all the components integrated on it. I'm going to show you some more concrete examples. What we provide to do acquisition of the signals from the real world is a MMIC, a monolithic microwave integrated circuit. And this is the Wikipedia thing. It's a type of IC that operates at microwave frequencies starting pretty modest. This is modest by our standards up to 300 gigahertz is the definition of a MMIC. So again, you get the flavor of what we're trying to accomplish. Real world, way up here, really high frequencies and high speeds. So what does that mean in terms of attributes that we have to go after? We've got to have much better gain. much better power than what you'd normally find in what you're trying to test, and we say roughly 20 dB better. That's maybe stretching it, but that's what we strive for. This one's really important. If you look through catalogs, you can often find designs that work in a banded way, over one particular Wi-Fi band or the television band or something like that. If you're providing an instrument to one of the laboratories in your school, you're not sure what you're going to have to measure as time goes on. You want the capability really of DC on up as far as you can go. And that's a different ball game. It's really hard to get a solution that will provide DC on up to those very high frequencies. But that's what you need for instrument type of mimics. High dynamic range just means a really large number of decades between the noise floor and how much power you can put into the device, the instrument, without saturating it, without overloading it or damaging it. You want that range as big as possible. And you don't want to distort the signals that you're trying to measure. And low noise helps you get this high dynamic range. If you're actually going to do this yourself, then whatever process that you come up with for making these mimics, it's got to be really reproducible, repeatable. We love this word in industry. It's called robust manufacturing. It just means that we use statistical tools and we get a very reproducible, predictable result so that the parts are always available when we need them. High reliability is another one that's super important for instruments. As I said, some of these solutions are very, very comprehensive and powerful in what they offer, but they can be very pricey as well. And if you get one into your laboratory and the professor tells you, gee, do a set of measurements, and you go, gee, I'd like to, but that thing that we bought from Keysight failed, that's not the name of the game in instrumentation. So that's the high reliability piece. The long platform life is important. The same argument. If you've paid a lot for these instruments and they're performing well, some of these things have been in the field for 10 years, 20 years, maybe even longer. And we have certain examples where some of our instruments have been in the US Navy ship, and they want it repaired. And we go, you can't be serious. This is 15 or 20-year-old technology. And they said, well, that catalog you left off with us with all your latest and greatest, we're not going to look at that until you repair the stuff that we've got already. So that's where the bullet comes from for this long. We're a captive supplier just to our instrument lines, and we'll support it as long as the line is shipping the instrument, 15 years, 20 years. And you don't get that with an outside foundry. They will give you an obsolescence notice. You got 6 months if you're lucky, and then that's it. It's gone forever. And the last bullet's important too. Where we operate in is a very, very high mix, but relatively low volume environment. So I'll cut to the chase. We have about 250 integrated circuits in production right now for our own instrument lines. And I'll give you a flavor of what they are in just a moment. And it would be nice if everybody in the world wanted a network analyzer on their desk at home, but that's not the case. Universities could afford them, the military can afford them, manufacturing operations can afford them, but you're not going to sell millions and millions of network analyzers. So what we need to produce for these integrated circuits or these mimics is basically the very best in the world, but we don't need a whole lot of them. So we work very well in this very high mix but pretty low volume environment that I'll be showing you. Okay, I won't go through these bullet by bullet, but this is an example for the ones that are in production, and perhaps the best way is just focus on the bold amplifiers up to 110 gigahertz, digital mimics, and digital by our standards are dividers, for example, dividing frequencies down from in units of 256 or 128 down to 16 or 2. These are pretty aging at this point, but they're diode types of structures that create a very sharp pulse edge that's important for sampling types of applications. A bunch of detectors, and the detectors are usually RF detection techniques, ways of detecting RF energy and then measuring it in the instrument or using it in a control loop. The need for mixers and multipliers we talked about, mixers for mixing down to lower frequencies, multipliers for going up in frequency in our sources. Limiters is interesting, and it's one that I'm involved with a lot. I'll try to convey to you how important it is for us doing these types of mimics to get the dimensions in the integrated circuit small and ever smaller. And when you do that, they become ever more sensitive to electrostatic discharge. And you have to take extraordinary precautions to get these intact into the instrument. And it's interesting where ESD can develop. It's real. I know you're dubious sometimes. Maybe you see in your lab, put on the wrist straps, but it's true. And especially as we shrink these dimensions down for higher frequencies. Switches, attenuators, often you'd say, if you're going through all this trouble to get a really sensitive receiver or a lot of power, why would you want to attenuate it? And it's because you want to put it in the middle of the measurement band, and you want to supply the right amount of power for the device under test, not overloaded. So attenuators are an important part of the instrumentation offering. And then modulators are ways of putting coding signals onto transmitted signals so that you can put a particular type of code that the cell phone would use and transmit that onto the line for testing. Okay, so this is an example of a PNAX. This has got 4 ports to it, and any of the 4 ports can either transmit or receive. And then in this particular example, it's doing, let's see if I can remember now, S parameters up here as a function of frequency. Also pulsed S parameters, intermodulation distortion up here, noise figure measurements, and this is a gain compression measurement. Are all part of the capabilities of the PNAX. And we have a bunch of contributions to the front end of this, the data, real-world data acquisition, mimics, thin film circuits we also make in our labs. These are much like ICs, but there's no active gain media. They've got resistors, capacitors, inductors, and paths to move the signals, but no way of actually amplifying. So often what you'll do is put a mimic onto the thin film to make it useful for our needs. A bunch of yttrium iron garnet spheres for filters or oscillators, and then precision mechanicals make reference to these connectors that have to be manufactured very precisely at those frequencies and ever smaller to make a cavity that will move the signal without loss. The types of mimics, I'll go into HBTs in a little bit of detail. Heterojunction bipolar transistor. The other type that we started with way back when was a field effect transistor as the active medium in the ICs. And a field effect transistor has got a source and a drain and a gate in between it. And if you want to try to get it to higher frequencies, then you move the source and drain ever closer together. in a FET. And in HBT, it's different. You're scaling in the Z direction. So you'll have an emitter, a base, and a collector. And as you scale these to ever higher frequencies or higher speeds, you're moving them in the Z-axis, not in the XY plane. And this is a very special type of field effect transistor where one of the semiconductor layers is strained, and this allows us to go even faster in that particular field effect transistor configuration. This particular example is 67 gigahertz, 4 ports. You can get up to 10 dBm from the ports and 110 dB system dynamic range. So it's RICs that do what? They acquire the real world signals right at the front panel and then convert down. Okay, high speed. I made reference to this a little bit earlier in that example of the oscilloscope. This is offered now up at 63 gigahertz. And in this case, it was a custom chipset that we actually fabricated in Santa Rosa, combined with some of our more traditional technologies in a specific type of packaging and microcircuit that then ends up on PCB boards and ends up in the configuration you see here. And I don't know if you've had the opportunity, but that's an eye diagram. And the more open the eye is, the more fidelity there is in the signal under test. And this one isn't so open. So it gives you an example of the type of analysis that's possible. The little inset up here is nothing remarkable. It's like what you'd expect from an oscilloscope, except if it was darker and we could see the legend on this, it's a 5 picosecond rise time on that pulse that's resolved real time by this oscilloscope. So not microseconds, not milliseconds, not microseconds, not nanoseconds, but picosecond, 5 picosecond rise time. Okay, so how do we fabricate these things? And what I'm going to try to do is use trade-offs as a way of trying to explain how we go about the fabrication steps. All right, so we saw this arrow of stuff of how the company is trying to align itself for our customers. Fortunately, it's kind of like what we do for Keysight internally all the time. We have very good IC designers. And hopefully that's what some of you will train in. They know how you put together circuits with microwave engineering principles. They've got this software simulation tool called ADS, and they work with the instrument labs, and they find out, gee, what's the most intractable problem that the customer is trying to solve? And then they will come up with a design that addresses that. We do prototype, which means examples. We actually fabricate prototypes of those integrated circuit designs. And it's what we call a pizza mask. It's got all different shapes and sizes of ICs on it. Runs through our same tool set as our manufacturing processes, by and large. And when they're done, the hardware lab and the IC designers will get together, much like you do in your labs, and they'll characterize them, run them through their paces, take them to the corner cases of safe operating regime, and they'll say, gee, you know, of designs A through M, design G looks pretty good. And that's the one that'll get put into production for the next 10 years or 15 years or 20 years, depending on how successful that design is. In manufacturing, I say here 300 plus ICs that are in shipment status, and we're trying to get tens of ICs into production every year from R&D. It is a 24-hour, 7-day-a-week operation in the fabrication area and also in the test area for both our operations folks and maintenance. And then the optimized part is we've got a pretty good support team of product engineers that try to support these as they leave our lines and go to our instrument lines for incorporation in the instruments. We do a whole lot of testing, but certain issues still come up because you can't test everything. Not everything is specifiable. And when it ends up in the actual instrument environment, it's more like what you'll see in the textbooks. There's all types of circuitry around our integrated circuits that can interact with it. So our product engineering provides the support, and in certain cases allows us to optimize back to, gee, it would be good if this design didn't oscillate the next time, for example, something like that. All right, so this is pretty dense here. In essence, it shows you in one block what goes on during the actual fabrication. So there's a bunch of processes where we've got expert engineers that are developing these process areas. And examples of them are shown here. Litho is short for lithography, which is the patterning of the integrated circuits. A bunch of different steps where the lithography is important. There's also dielectric depositions, so silicon dioxide, silicon nitride. There's also metal depths and ways of depositing the dielectrics called plasma-enhanced chemical vapor deposition and so forth. So there's 13 process categories here, a bunch of different process types, over 100 different process tools to make those processes happen, and then we try to monitor all of those with statistics. Okay, so now cutting this way, what is that about? And those are the different product families that we support. So some of them could be field effect transistor families, some of them are heterojunction bipolar transistor families, some of them are diode families. And for each one of these bars, there's an integration engineer that's responsible for that particular platform. And the integration engineer does what the name implies. They make sure that all of these processes are working in concert to produce, from their point of view, test arrays that are on the wafer that are well within the statistical control limits. They never actually care, per se, about the circuits that are in that IC platform. They don't so much care whether it's a mixer, a modulation type of IC, a divider. They just want to make sure that all of these processes are working well in concert to make transistors with the specified properties. It isn't until it leaves the fabrication process where we get to test that now for the first time you're actually turning it on to do the real process work. Does it really amplify? Does it really divide? Does it really mix? Does it really detect? And our IC test area is concerned with those functions. And we do DC, frequency, and time domain characterization as needed. And as I suggested, we spend a lot of time concerned with the reliability and all types of tools to try to characterize the transistors that come from the process and forecast how they'll do in the instrument application over time. And I won't, this is high temperature operating life, this is medium scale integration. This checks out for wear out as it would occur on the bench. This is infant, so in the first 6 months, with large numbers of transistors, is there a weakness in the transistor that can be filtered out? High voltage sounds like, gee, do you ever have high voltage with ICs? And it's relative, right? I mean, you'd bias these between 5 and 20 volts, but sometimes 20 volts can be a high voltage type of stress. High current, this is electromigration. This is where the metals in the IC will mix due to moving current. Radio frequency operating life is exercising the transistor over its complete range as you would when you were doing an RF type of amplification, and that can lead to very distinct types of failure modes. And this is back to high voltage again. In half the cases, The actual ICs end up going to the instrument lines as chips, and I'll show you some pictures of those, and then put into high frequency, we call them modules or gold bricks. The other half, we actually package them into surface mountable components. So it's about 50-50, and so we've got a set of engineers that are just concerned with the packaging for surface mount application. Now you can check me as you go through the slide set, if I defined all the terms. So I did try to go through and make sure.
What kind of yield do you achieve?
Yeah, good question. I had that same question from the company CEO, and I said it can be very good for processes that are mature, that have been exercised over a long period of time. But if they're more in the category of what I called before bleeding edge technologies, they can be very poor. So as good as 98% at electrical test, as poor as 0. And our CEO said, what? Sometimes they're 0. Often for reliability types of concerns. And the reliability testing, even as you see from this flow, it takes place at the worst possible time. You've spent all the months to do these process steps. You've done all this IC characterization, and then you pull a few test arrays off the wafer and subject them to some of these reliability screens, and it fails. And all of that effort is for naught. And one of the vice presidents said, well, wouldn't it be smarter to do your reliability test back here somewhere? And the answer is, if we knew what to do back there, we would, but we don't. You've actually got to go through the entire fabrication and then test samples from each wafer. And we've been doing this for a long time. Some of them are on an audit basis where you just do it every month. Some, to this day, every single wafer we produce, you do reliability. Okay, so 3-inch diameter wafers. And you can see someone using a vacuum wand to pull it out of the cassette. 3-inch, you'd say? I thought silicon is up at 12. And the answer is we don't need a whole lot of them. We just need the very best. This is our bay for dry etch and plasma-enhanced chemical vapor deposition. This is one of those kind of ones that the kids take, like a fisheye lens, where you see around the corners. This is our deposition bay with our electron beam evaporators. And this is our lithography bay in one of these wraparound figures with lighting that's filtered so it won't disturb the photosensitive chemicals. Okay, so, I'm sorry. One other thing I should have said on this one is this is the first one where I've got a slider. So we do internal fabrication. Some of these capabilities are available in foundries, typically overseas. This is actually here up on Fountain Grove Parkway. And the reason it works is what we've been talking about this whole talk. We do just state-of-the-art, high reliability, and we support these products as long as the instrument line needs them with no fear of obsolescence. The other trade-off in this one is we do mimics. So some of this functionality you could do with individual components, try to link together what's called a hybrid solution. But integrated circuits is the way you go, especially at these high frequencies, because the characteristic length at these high frequencies is very short. So this is an example of one of our ICs, and what's important for you to realize on this is this blown up picture is like if the IC was like this table, it's looking down on the surface of the IC. And when you see a cutout, like you see over at the right of a via, it's going through the wafer. So this is the surface of the IC. It's got, it's indium phosphide based. It's got integrated resistors, capacitors, ESD diodes, and these backside vias, which are in these positions. And this is the way you do grounding at very high frequencies. It's a via, a channel, a tunnel, that actually goes through the IC from front to back side, and it gives you very low inductance ground path. And it's one of the attributes that are attractive about the types of processes that we support. This particular design is one of those ones used in the oscilloscope, and there's about close to 500 transistors in this IC. I didn't go through and count them, but the designer did. And there's about 565 of these on a 3-inch wafer in this particular case. And this is an example that we see over here of a via. The part that we see on the front side is here, and it's about 100 microns to the back side of the wafer, and that's all plated gold to make that connection. So, mimics is one of the design choices that we do. The types of transistors that you're seeing in this type of IC is a heterojunction bipolar transistor, and I'll go into that in a moment. We offer field effect transistors, but not on the same IC or on the same wafer. So it's a choice the designer's got to make. Do I want to design in FETs or do I want to design in HBTs? Not necessarily true in the silicon world, but it is true for ours. And diodes are often used for the ESD protection. And we've talked about resistors and capacitors and inductors. There are 2 or 3 layers of metal interconnect used in the IC, which is modest by silicon standards, but it's enough for our high frequency designs. Okay, this is a trade-off of, we do our own fabrication up on Fountain Grove Parkway. We do it as ICs. Why do we go through all the trouble to do compound semiconductors instead of silicon? And I'm trying to show this graph, show the reason for that in this graph. And it shows how high you can go in frequency with the transistors in a number of different processes for unity gain, and the breakdown voltage. So this is, if you apply voltage to the collector and the emitter, you start going up in voltage. At some point, it's going to break down. So in the silicon world, over the past 10 or 20 years, they've made significant advances in going to higher and higher frequencies. And the way they do that is not only pure silicon, but they blend in the next element down in the periodic table, which is germanium. And this allows them to get this type of frequency response, which is extraordinary, but the breakdown voltage is very low, just based on silicon germanium crystal structure. And for instruments, that's not desirable. In instruments, you want not just logic levels like you'd use in processors or memory, you want power to the front panel, or very large amounts of power going to the mixers. And so fortunately, there's alternatives. If you use compound semiconductors in a single heterojunction configuration, which I'll explain in a moment, you can get much higher breakdown voltages for pretty high frequency ranges. And in another configuration called double heterojunction, you can get, again, these high breakdown voltages at still higher frequencies. And our highest performing technology at the moment is right here. It's called heterojunction bipolar transistor 2B is the terminology. So there's some summary information on compound semiconductors and silicon germanium over on the right. But basically, this works real well for instruments, and it's what we use in our labs. So that's why we're all the way over to compound semiconductors. Modest integration levels, just hundreds of transistors, but it's got the breakdown voltages that will give us the power we need for instruments. And we get away with 3-inch diameter wafers. Silicon, it's got very, very small dimensions. They use lithography techniques that we don't have access to here in Santa Rosa. So instead of just 125 nanometers, they're down to 45 nanometers and going even lower, using very expensive lithography techniques, massive integration levels, high speeds that manifest themselves in these high frequency responses, but a different market, a different use for them. and 12-inch diameter wafers. So what's interesting is, 12 inches in diameter, when you put a number of those together in a cassette, it's too heavy for a human to lift, or at least a normal human, and they have automated lines for all of the processing. This is a cross-section that's in the literature for one of our heterojunction bipolar transistors. So there's a number of points on this one. The semiconductor layers are shown on the left. The metal and dielectric layers are shown on the right. This business about compound semiconductors, here's silicon, here's germanium. What we're using is column 3 and column 5 is our compound semiconductor. So gallium arsenide, aluminum gallium arsenide, indium gallium arsenide, any combination of 3 and 5. And you'd say, well, how do you pick? And it's called band gap engineering. You pick those to give a band gap that's appropriate for the device that you're designing. I don't have time to go through the actual process flow here, but you can imagine it in the following way. These are the semiconductor layers, a portion of them. And in the original device, there's a couple of more up here. What we do is we start at the top with the emitter metal, and then etch away a mesa around it. The next piece that's fabricated are the base connections, and then you etch away even further and put in your collector contacts. And the important point about this is if you're trying to do 500 transistors in each IC, and you've got about 500 of those on a wafer, you don't do this one at a time. You do it for all of the emitters at the same time, then you do your bases all at the same time, and then your collectors all at the same time, and then you interconnect them. We do all the processing on the front side, flip it over, We do all the processing on the front side and then do tests of the transistor characteristics. Then flip it over and do the backside processing and then ship it to the IC test area for testing as circuits. There's about 18 mask layers in this, and it takes about a week at normal priority to do a mask layer. So you're talking 4 months, 5 months to do a run of this type of wafer. Professor Kajori worked at Bell Labs. They invented molecular beam epitaxy. We use that for some of our semiconductor growth. A very excellent vacuum chamber with the sources underneath. We also purchase metal organic vapor phase semiconductor material. Another trade-off is, this says high current density, but basically it's saying to get to high frequency or high speed, you got to make your dimensions small. And the way that it's perhaps understandable is if just think about capacitors. If you had 2 plates and you wanted the transit time from top to bottom plate shorter, you'd bring them ever closer together. But what happens then? The capacitance goes up. If you're trying to keep the RC time constant small that you're working with, as you bring those plates together for shorter and shorter transit time, you've got to cut down the area of the capacitor. And when you do that, by definition, the current density is going up. So from our earlier generations to our more advanced ones, we're going to smaller and smaller dimensions and higher current density. But the good part is that the maximum frequency of response goes in a favorable direction. Lithography is patterning. We use a stepper type of technology with a mercury lamp that shines through a mask and then focuses on the photosensitive chemical coated wafer. This is an example of the emitter metal going down with resist around it, and metal that you don't want ends up on the resist. Metal that you do want for the emitter is shown here, and then we use a lift structure that just floats that metal off. Deposition, all of the different ingredients that you'd need for an IC, both metals and dielectrics, with the tools to do it. Dry etching means you use gases. With a plasma, wet etching, just dip. And then when you're done, you get something that looks like a little city. This is a very magnified SEM View. of a couple of the transistors in one of these ICs and the interconnects on different levels. And the engineer that provided this picture a while back at this time used fuming nitric acid to remove the dielectrics to get that picture. When you're done, if it's a prototype mask or a pizza mask, you would use a laser to do the separation following each IC. If you saw it, you'd cut through the other guy's design. In production, we do separate by a dicing saw, a diamond dicing saw. Finally, in terms of testing, there's a laboratory just for folks that are doing design and development. This is an area that we do production testing, and a whole area in our basement to do reliability stressing. So these are little chambers with high temperature to simulate what you get in an actual instrument environment. We do all our testing, most of our testing in wafer form, not in chips or packages. We do testing in packages, but the heavy-duty testing is here on a wafer. To do that, you've got to get probes, and this is an example of what it looks like with probes going on the wafer. We don't just do all of that work to fabricate the wafer and get probes down just to see, gee, does it turn on? We do full characterization using a whole suite of Keysight test instruments. We've got them up at high frequency, how much power, how much noise, using the full capability of our own instrumentation to characterize. Parametric testing is what we call it. And these are examples of frequency up to very high gigahertz, dividing the minimum power that's needed up to 65 gigahertz, and more of what you'd see in one of your laboratories, the Gummel types of plots of the transistors. This last one's a little bit hard to see, but as I said earlier in our discussion, we don't stress the actual ICs, but test patterns, individual transistors, because you can look at the Gummel plot, for example, and see how that's changed. So we use arrays, discrete transistors, sometimes just 4, sometimes 200 strung together to simulate what happens with infant failures. You need to look at large numbers. If you've got 1 in 10,000 that could fail, you need large arrays, medium scale integration. And this is some of the plots that come from high temperature stressing of these arrays. So the last topic is future needs, and these are pretty soft, but probably pertinent to you. We need faster time to market. We need even higher frequencies and speeds. And as I said, that last piece of that equation that was in the beginning, people, we need engineers in all these different flavors. Electrical engineering, materials science, chemistry, physics, computer science, mechanical engineering too. And they're hard to come by, the people that enjoy this type of work. And then we also entertain university and government collaborations. There is a whole department that tries to coordinate our university partnerships. There's a program that's just been announced that I've got a handout if anybody is interested that talks about being certified in electrical measurements. And then these are some of the references that have come out recently with collaborations with the University of Sheffield, University of California, San Diego, and China. And finally, in the last slide here, it's one of our Keysight engineers with engineering department head accepting some of the older Keysight equipment. And your department head says that he highly appreciates Keysight's continuous support of the EE program. Our intention is to use the donated equipment for our new RF lab. The introduction to RF course will be offered in the spring, and having access to the equipment will be very beneficial for the students. So, we went through these topics. We're probably at pizza time, but please catch me, and I'll try to answer any questions that you may have. Any quick ones? Yes?
2 questions.
Yes.
One, other than internally, do you have external customers for these ICs?
Very little, 1% or so. And more of what we would call strategic partnerships. And the reason for that is the folks that we supply these integrated circuits to within the company say, distraction, you focus on my needs, what my instrument needs to get to the market quickly, don't distract yourself with the outside stuff. That's part of it. The other is, if you offer ICs to somebody like, let's see, AT&T, I guess, Lucent Alcatel, and you're shipping them these ICs, and there is an issue where there is a shortage or low yield, and you say, gee, you're not going to get your ICs on schedule. They'll go, oh, that's interesting. You know all those network analyzers that we ordered? Forget it. Just keep them there on the dock until we get our ICs. And it's a tough way to make money. So, go ahead.
How about the competition? Is there a competition?
There's two types of competition. The foundries that make these types of integrated circuits are really targeted towards cell phone, large volume types of operation. The other sort of competitor is for the instruments, and those are the real competitors that gain most of our attention, and they have different sorts of ways of getting value to the customer. It's very rare to have an internal fabrication facility that will do the designs that the designers come up with to meet the instrument needs. It's almost unique in the industry. So one alternative that you could try is I'll just buy a whole lot of what I can get from the foundries and measure them all, and then pick the very top 5 or 10% and try to use that for my instrument. But it's tough way to make value that way.
Yeah, okay, yeah, good. Now I ask this. Okay.
Would only take a second. One of the very last slides, you talked about the future needs.
Yes.
And how Agilent was in need of qualified people. But the question then arises, for a new graduate with a bachelor's degree, how prepared are we? All of our instructors have PhDs. You yourself have a PhD. Most of the people over there probably have advanced degrees. So when you say you need people, and we get out here with the bachelors, what do we do then?
Yeah. So I would say it depends. One of the reasons I put this up is, one more. And I won't. So if you're going to do design, yeah, I don't argue with you. It's tough. You do need PhDs from one of the design schools to be successful. But fortunately, in this type of work that we're doing up on Fountain Grove, there are areas, we hire bachelors. And the most effective way, if you want to get into that type of work, is to do an internship. And you just look on the home site, at least of Keysight, and you will see internships advertised for the different areas within the company, not just our own. And it's a great way and internships are for folks that are in undergraduate school, can be. Sophomore year, junior year, senior year, through graduate school. It gives you an opportunity to see the kind of work we do, and to be honest about it, gives us a chance to see you, and it's great. You can find extraordinary candidates that way. So yeah, for design, maybe not, but process, test, reliability, product, we hire bachelors, not exclusively, but we do hire them.
Thank you.
Now, I have a quick question. Basically, if Keysight technology makes products which can measure.
Yes.
Now, in order to measure something, your equipment that measures your own thing and so on should be maybe an order of magnitude, have a better accuracy and also a resolution type of capability. How can you assure that you have such a thing to be able to measure your own thing to say that, okay, yeah, that's really good and does its job?
Yeah, so I think there's probably two parts to your answer, and I have gotten in trouble answering this one before, but and Don could probably help me on this. One of the old ways that it used to go at Hewlett-Packard was we'd say, we're designing for the engineer at the next bench.
Yes.
whatever problem they're working on, we'll make an instrument that can help him solve his problem, which then could be used back on this bench. So it's called designing for the next bench. And that does go on. Those big racks of test equipment that you see in our test area, we are waiting, well, it just came in a couple of weeks ago, a prototype from the instrument labs that we need to measure our latest integrated circuit. And we had to wait and wait, and there was no other choice. There was no other way to do that measurement. When it finally arrives, we leaped on it and performed what had to be done. What's still in the process of that. The way I get in trouble with that answer is they say, well, how do you know it's calibrated correctly and precisely enough? And we've got pretty rigorous tools for making sure that even these prototypes from the instrument lab go through a bunch of different product life cycle tests, releases, transitions we call them, to try to ensure that we really are meeting the data sheet for the instrumentation. So it's a trade-off. We want the very best as soon as we can, but we don't want junk either.
So I would like to thank Dr. Kellert for giving us such a good lecture. Basically, let me tell you, a few days ago, he sent me his the slides and so on. In fact, I want to send them to you for your report. But when I looked at it, I saw that, oh yeah, this is something that really would be beneficial to you guys. Why? Because he basically went through a number of, shall we say, characterizing parameters that we, as engineers, we need to understand, especially in the high frequency type of thing and so on. All of these, how do you characterize, a piece of, a measurement equipment or whatever? These are the things that I really liked about the talk, and I learned a lot after it. So let's give him a hand there.